Hi there, welcome back to another video. In this one we're going to prove that the sum of the first n natural numbers is this thing here, n times n plus 1 over 2. Now we're going to prove this two different ways. Firstly, we're going to use mathematical induction, and this proves it for all n. Secondly, we're going to use a little algebraic trick, and then I'm going to draw you a picture and actually explain what's going on. So let's start with the induction. Right then, for the induction we start here. So this is the statement we want to prove. For all n in the natural numbers n, 1 plus 2 plus 3 plus up to n equals n times n plus 1 over 2. Now as with any induction, we start with the base case. So the base case for the natural numbers is just n equals 1. So what we do is we plug this into the left and right hand side. On the left we're going to get 1, and on the right we're going to get 1 lots of 1 plus 1 divided by 2, and this right hand side is equal to 1 as well, because you get 1 times 2 divided by 2. So our base case is done. Right, inductive assumption. So assume the result is true for n equals k. Assume true for n equals k. And I know a lot of people would just say assume true for n, but I quite like to use a different letter. It sort of makes it clear to me. But everyone has their own ways. So assume true for n equals k, that is 1 plus 2 plus 3 up to k equals k times k plus 1 over 2. Right, so that was our inductive assumption. Now let's move on to the inductive step. We consider when n equals k plus 1. So let's have a look. Well, 1 plus 2 plus 3 all the way up to k plus 1. Okay, well, this is the same as 1 plus 2 plus 3 all the way up to k, and then plus k plus 1. Right. Now what we can do is use our inductive assumption, so this bit here. So let's do that. So we can say this is equal to, well, k plus 1 over 2, but we've still got this term here, plus k plus 1. So I'll write by inductive assumption. Okay, so this is where we're up to. We've got k times k plus 1 over 2 plus k plus 1 is equal to our sum of the first k plus 1th natural numbers. Right, what can we do now? Well, we can make the denominators the same. K plus 1 over 2 plus 2 lots of k plus 1 over 2. And then we can join the numerators. So this is k plus 1 plus 2 lots of k plus 1 over 2. Okay, great. Now we just need to do a little bit of expanding. So this is k squared plus k. And then the right bit we've got plus 2k plus 2 divided by 2. So by expanding. Right, and now we can see that this is k squared plus 3k plus 2 divided by 2, and we can factorize this. So if you look at this for a minute, you should be able to see that this is k plus 1 times k plus 2 over 2. And this is exactly what we wanted to show. So we've shown that 1 plus 2 plus 3 plus k plus 1 equals k plus 1 k plus 2 over 2. So to finish, we'd write hence the result is true for all n and n by induction. Okay, that's the end of the induction proof. Okay, now we'll move on to proof number 2. So this is our thing we want to prove, 1 plus 2 plus 3 all the way up to n minus 1 plus n. Now what Gauss did to prove this is he looked at 2 times s. or rather just s added onto itself, but he did it in quite a clever way. So let's have a look. So we've got that, and then we're going to add s onto itself, but we're going to do it like this. So we're going to go backwards. So we're adding n plus n minus 1 plus, I'll do it completely for clarity, plus n minus 2 plus 2 plus 1. So now what have we got? Well, if we add these column by column, we've got 1 plus n plus 1 plus n again, plus 1 plus n, plus 1 plus n, plus 1 plus n. Right, and I'm good, just for a bit of clarity, I'm going to rewrite this as n plus 1 plus n plus 1 plus n plus 1, and so on. N plus 1 plus n plus 1. And hopefully you should be able to see that there are n of these, n times. So this gives us that 2 lots of s equals n times n plus 1. Right, so we're nearly there now. All we have to do now is say, well, 2 lots of s equals n plus 1. And this implies if we divide by 2, s equals n times n plus 1 over 2. Okay, great. Now I'm going to draw a little picture and explain what this method actually does. Okay, so here we have an example and we're showing how the proof in the second case actually works. So we're just doing it for a very small n, so n equals 5. So we're looking at how to find the sum 1 plus 2 plus 3 plus 4 plus 5. Now I've drawn a little diagram here, and in this diagram each blue square represents 1 unit square of area. This means that the area of all these blue squares is what we're looking for, 1 plus 2 plus 3 plus 4 plus 5. Now hopefully you recall from the proof that to actually prove it, we added n to 1, n minus 1 to 2, n minus 2 to 3, and so on. So what I'm going to do is add these number of squares onto the row now. Okay, fantastic. So I've gone ahead and added 5 squares to row 1, 4 to row 2, 3 to row 3, and so on. So now this is a rectangle which is 2 lots of our sum. Now you should be able to see that the width of this rectangle here is 6 and the height of it is 5. Okay, and we all know the formula for area of a rectangle. Remember, the sum we're looking for is the area of the blue squares, so all we have to do is find the area of the rectangle. Area of rectangle, well, that's just length times width, which equals 6 times 5. And then what we're looking for, which implies 1 plus 2 plus 3 plus 4 plus 5 equals 6 times 5 over 2. And hopefully that sort of makes sense as to what that proof is doing. So essentially it makes a rectangle, we find the area of that rectangle, and we divide by 2. Okay, hope you've enjoyed this video. Give it a like if you enjoyed, and thanks for watching.